Right, so our next intermolecular force is the dipole-dipole force, but before that, let's just take a quick review here. And so we've got our picture here of our periodic table, and then remember, as we go towards the top left, we increase capital EN, which stands for electronegativity. And electronegativity, remember, is the measure of how strong a nucleus pulls on electrons within a bond. So, for example, if we have this molecule right here, formaldehyde, we have this carbon-oxygen bond. Right, we've got a bond between carbon and oxygen, and if you think about the periodic table, the oxygen is more electronegative than that carbon. And so if we think about the distribution of the electrons in this molecule, they're going to be pointed towards that oxygen, right? This is going to be a polar molecule. Think about, our previous content or the beginning of the semester. And so if we think about how this molecule is going to arrange itself with another molecule of itself, they're going to maximize the positive and negative attractions. So for example, if we had another molecule of this one also has that same dipole. And so we have an attraction between this partially positive oxygen and this partially negative oxygen and partially positive carbon, right? So we have an attraction between dipole forces, right? So hence the name dipole-dipole force. You can think about this as kind of like two magnets coming together, right? They're going to point with the north and south ends attracted to one another. Same thing here. And so the difference between a London dispersion force and a dipole-dipole force is that in the dipole-dipole force, we have a permanent dipole, right? Because we have a polar molecule. So this is a polar molecule, which means that it has a permanent dipole. And so we can see that this intermolecular force, again, is an attraction between positive and negative ends. This force is indeed stronger than the London dispersion force because it's a permanent dipole. And this is just another image of it, right? We can see we have a partial negative on the oxygen, partial positive on the back end of that carbon. And same thing, this is what this is showing as well, right? The red is a high electron density and then the blue and green is a lower electron density. And we can see that opposites attract. One thing we have to be careful about dipole-dipole forces, and when determining whether something has a dipole-dipole force, is to think about our bonds, right? So for example, formaldehyde, we have a polar molecule. This over here is ethane. Remember that carbon-hydrogen bonds are nonpolar. The molecule on the right has no permanent dipoles. The molecule on the left does have permanent dipoles. If we take a look at the molar masses, they're approximately the same. So this one's 30.0 grams per mole. And then this is 30.1 grams per mole, right? So any difference in the boiling point is not going to be due to a difference in the mass or the size or London dispersion forces. It's only going to be due to the difference of whether they have dipole-dipole forces or not. And so if we think about the boiling point here in degrees Celsius, this formaldehyde is negative 19.5, while ethane is negative 88. So we can see that the formaldehyde, the molecule on the left that has the dipole-dipole forces, has a much higher boiling point, right? And that's because these intermolecular forces are keeping the molecules together and preventing them from being turned into a gas. These dipole-dipole forces explain a lot of things. So it explains why oil and water don't mix. So oil itself is basically just carbons and hydrogen, so it's very nonpolar. While water itself is oxygen and hydrogen, and that is very polar. And so basically what happens here is that the polar molecules kind of want to be with themselves due to this attraction. right? They're going to arrange themselves to maximize this dipole-dipole interaction and thus excluding any oil from that. And then one thing you have to be careful about whether determining a molecule has dipole forces or does not. We can't just look at the types of bonds we have. We have to also think about the shape of the molecule. So for example, something like carbon dioxide does have polar bonds, right? This oxygen is more electronegative than the carbon, and that those are indeed polar bonds. However, carbon dioxide has a linear shape, and so these charges cancel one another out, and so they're non-polar. Remember, when the dipole arrows within a molecule face in opposite directions, they cancel each other out. Whereas something like water has a bent shape, right? And so we have two dipoles here, and so we have a net dipole that points up. And so water is indeed a polar molecule. So again, in order for something to be a polar molecule and thus have dipole-dipole forces, it needs to have polar bonds, and these polar bonds need to face in approximately the same direction.